We're moving on in our sub-series of advanced routing videos as we look at manipulating route updates. Now, by design, routing protocols send routes, and they send them to all of their neighbors, all of the neighboring routers. And that's what we want most of the time. We want a full routing table. We want to be able to reach everywhere on our network. But there may be instances where you don't want some of the networks to be seen. For example, maybe you were connected to the internet and you want some of your public routes to be advertised out, but whoa on the private network. So we want to filter those before they go out to the internet. Maybe you're with partner organizations and you want some DMZ subnets to be advertised to the partner organizations, but not your entire network. You don't want that out there. That's where manipulating route updates comes into play. 3 topics we've got lined up here: distribute lists, route maps, and boy, that could be 90 topics in one right there. And then finally, administrative distances. These are the 3 ways that we'll talk about that we can manipulate route updates between our devices. All right, well, let's start off with the simplest of these mechanisms, and that is distribute lists. The key word is lists because I want you to associate in your mind distribute list with an access list. That's exactly what it allows you to do. It allows you to apply an access list to routing updates so that when the router decides, well, let me just send a routing update out this interface, it's going to say, oh, there's a distribute list there. Let me check it to make sure all of these entries are allowed to go out that interface. So for example, you see my little 2 router network down at the bottom. We've got this router over here on the left that's got 10.1.1, 2, 3, 4, all the way up to 255. When it sends an update out, based on the interface that it goes out, we'll say it's serial 0 down here. It's going to check and say, is there a distribute list applied to that interface? If so, I'm going to check that distribute list, which is tied to an access list, that will give me a list of allowed updates to go out. So maybe 10.1 isn't allowed, but all the rest are, because 10.1 is some subnet that you don't want people to know about. Now, these distribute lists can be applied inbound or outbound under a routing process. Now I want to make sure I emphasize these 4 words: under a routing process. The reason why is because I just said it's going to check it when it goes out the interface. Well, that's true, but the filter isn't applied to the interface. It's applied under a routing process. So I would go under, say, router RIP. And under the routing process, in the config mode, I've got the little pound symbol, blinking symbol right after config-router. I would type in distribute list, blah, blah, blah. And then I would type in an access list number, followed by the interface I want to send it out of, or inbound. So I can filter when the routing updates are being sent out in interface, or I can filter as the routing updates are coming in interface. Is that clear? So that the router really has the ability to stop updates from coming in or keep them from going out to their neighbors. Now, this does work slightly different with OSPF and ISIS. The reason why is those are link state routing protocols. It is a requirement of link state routing protocols that all of the routers in the same area have an identical link state database. So if we were to be able to filter those and change the link state database so that this one had a different one, filtering some of the routes within an area, then it would totally defy the rules of link state routing protocol, which we can't do. Instead, a distribute list with OSPF and ISIS keeps the routes from moving from the link state database to the routing table. Okay, so this router maybe has a distribute list applied inbound, and, as it comes in this interface that says, do not allow the 10.1.1 network to come in. Well, because it's a link state routing protocol, it's got to come in. It's got to go to the link state database. But this distribute list keeps that route from ending up in the routing table. So it's kind of funny. It's like the router knows about it, but it's like, I'll pretend that I don't, right? Just so that it kind of pretends that it doesn't know about that network and it won't be able to route to it. Now also, with OSPF and ISIS, since they are link state routing protocols and they all have to have the same link state database, there is no such thing as an outbound filter. You can't prevent routers in the same area from sending the data to each other. You can just prevent them from putting it in the routing table. Let's move this into a practical example. We've got two routing domains on the screen, RIP and OSPF. Now over on the left-hand side is router 1, which has a plethora of networks. Maybe those are just different VLANs within a certain location that are being sent via RIP over to router 2 and eventually would like to redistribute into OSPF. But the catch is that some of the VLANs that we have behind router 1, we don't really want to get out to the entire organization. Some of them are just meant to be local VLANs that, host private accounting servers that no one else should be reaching other than the people behind router 1. And that happens to be the 10.50.1 and 2 subnet. So I want to make sure that the 1 and 2 subnet don't reach router 2 at all. I just want that to remain local to router 1. Now the 10.50. I should document this, right? So 10.50.1 and .2 should not reach router 2. So those need to stay local with router 1. Now, furthermore, 10.50.3 and .4 is something that is for this division of the company only. Whatever this RIP domain over here is, they are the only ones that need to know about 3 and 4. So in addition to filtering 1 and 2, when I redistribute those RIP routes over here to OSPF, I also want to make sure 3 and 4 don't make it across, but 5 through 10 can. So let's check out the action. I'm going to start off on router 2 sitting right in the middle. Just do a show IP route to prove that there's no filtering in place right now. You can see I have one OSPF route coming from the right side of the network. That's just a WAN link, it looks like. All the others, 50.8, 9, 10, 1, 2, 3, all the way down here, are being learned via RIP from router 1, which is this IP address right here. Now to start things off, I'd like to do the filtering at router 1. Notice I have the interface, serial 0.2, right here on the diagram so that we know what interface is connected over here to router 2. So let's hop on over to router 1, and I'm going to do a show IP protocol just to verify RIP is running. It's routing for all my loopback interfaces, which that's really the quote-unquote VLANs I was talking about. I kind of blew my cover there. So it's sending those networks over to router 2. I'm going to filter it down, and the first thing I need to do is create an access list. In my opinion, it's easier if you create a standard access list, but it will work if you want to do an extended one. It just gets a little bit more complex. I like named access lists. They just make a lot more sense to me. So I'm going to type in IP access list standard, and let's name this guy route filter. Enter. Now underneath here, my goal was to block 10.50.1 and 10.50.2. So let's do that. I'll type in deny 10.50.1.0. And I'll hit the up arrow and 10.50.2.0. Now remember, an access list that just has deny statements will deny everything because it has the implicit deny at the end. So let's finish this one up by typing in permit any. So at this point, I'll type in a show access list just to verify my configuration. There's my route filter. I see deny 10.51, 2, and then permit anything else. Now to apply it. I'm going to go under the router RIP process. Now we're sitting on router 1, right? Just want to make sure we're clear on that. Serial 0.2 connects to router 2. I'm under the router RIP. I'm going to type in distribute list, followed by the access list number or name that I want to apply it to. So I'll say distribute list, and I'll put route filter, which is the name of the access list that I put up here. Before I go on, notice I can also filter based on prefixes on routing updates or from a specific gateway. I don't have to do it per interface. I can just say, well, for that neighbor, I don't want to send these out. But for now, we'll do it on the interface basis. Now I put in the distribute list route filters. Now it's saying, are we going to filter the incoming or outgoing route updates? Well, let's look back at the diagram. This is going from router 1 to router 2. It's advertising all these networks, so that would be an outgoing update going this direction. So I'll say distribute list route filter out, and then hit a question mark. Now notice I have a bunch of options. I have all these interfaces that I can type in here, but I also have a carriage return. If I hit enter, the route filter immediately applies to all interfaces. I just filtered the entire routing process, so they no longer know about that route update. But instead, I'm going to say route filter out serial 0.2, which is the interface that connects up here to router 2. Now let's jump up to router 2 and check our work. I'll do a show IP route. Now, there is a catch. I'm filtering 10.50.1 and .2, right? Those are the two. You notice they're still there. But remember how RIP works. It sends an update once every 30 seconds. And it's going to maintain these route entries unless I clear them out. So I'll do a clear IP route star, which just flushes the routing table. And let's do a show IP route one more time. See if it picked those back up. Ah, look at that. We've got the 10.50.10. Oh, 3, 4, 5, 6, 7, 8, and 9 up here. 1 and 2 are mysteriously missing because our route filter has gone in place. It's gone in action. Router 1 is keeping those updates from ever reaching router 2. Now, we could have done the same thing by applying the distribute list inbound on router 2. I just figure it's better to filter it at the source. Closer to the source you are, the more efficient you are in this case. So now you've seen filtering using distribute lists when it's applied directly to the routing protocol updates coming from a router. The other place that you can apply the distribute list is when you're doing redistribution. Now remember our scenario, we wanted to send the RIP routes into the OSPF domain, and as of yet I'm not doing that. So let's jump under the process. I'll do router OSPF1 and just do a flat redistribute RIP. We'll do the subnets that were being sent. I'll do the metric of 10,000. We'll keep the default metric type of E2 routes. So let's that should send all those routes from router 2 over to router, let's see, 3 and 4 over there. So let's just verify that's happening first. Hop over to router 3, show IP route. And sure enough, there they are. The RIP routes are coming through. Type E2, a metric of 10,000, just like we said. And we are missing our requirements because we said we wanted to filter route 3 and 4 out of that list. You can see that from keeping them from going over to OSPF. So let's make it happen. The way we do that is we go to the router that we're doing the redistribution on. That's router 2. Just like before, distribute lists always relate to an access list. So we need to create an access list saying what we want to permit or deny. So we'll do a IP standard access list. Let's name it route filter 2 in this case. And I will say I want to deny the network 10.50.3.0. That's our 3 network. And 4.0. Let's add that into the mix. Permit everything else. Exit out of there. Now I'm going to get under the router OSPF1 process, and this is where it gets a little bit weird. We've done the redistribution already, so now we need to apply a distribute list. Just like before, I'll type in distribute list, followed by the route list name. I'll say route filter 2, and when I say route list, I meant access list. And then I'm going to say that is going to go in the outbound direction, meaning as it goes out to the OSPF domain. And this is where we'd normally come in and say and apply it to this interface. But instead of applying it to the interface, I'm going to apply it to the protocol that is being redistributed into OSPF. That's where it gets a little weird for me. It seems like I would go under maybe RIP and say keep these from going to OSPF, but instead I'm going to go into OSPF and say keep these RIP routes from coming over here. So in this case, I'm going to say route filter 2 out from the RIP protocol, enter. I was thinking there's one more thing after that, but that's it. I'm going to say out from the RIP protocol. Now that's weird to me just because it seems odd to go under the OSPF and refer to the RIP protocol because it seems like the redistribution command would make them OSPF routes, but that's not how it works. It does make them OSPF routes, but since we're on, I'm just going around in circles here. I'll tell you what. Hopefully that makes sense to you. It's a weird one for me. You have to get used to applying it to the routing protocol that you're sending into OSPF. And it knows you're going into OSPF because that's the routing protocol we're under. That was a moment for it to soak in. Okay, now I'm going to jump back here. It was more for me than anybody else. So that's where the distribute list is applied. Let's do a show IP access list. Just want to verify the route filter's happening and check that out. We've already got a match on each of those deny statements. 7 matches on the permits. My guess, that might be the other routes that it's sending across. So now we should be able to go to router 3 and verify that this has happened. No need to clear the IP routing table. It happens right away. Do a show IP route. Beauty. 10.50.3 and 4 are mysteriously missing from the list. They were caught up somewhere around here in that deny statement. So distribute lists can be applied directly to the routing updates, or you can apply them to the routing protocols as they are being redistributed into other routing domains. Now we get into a much more flexible but complex method of route filtering, and that is route maps. It's more complex because route filtering is just one of many capabilities that route maps have. They are going to be primarily used when we get into BGP. So I don't want you to think that this is all we're going to see of route maps. We'll see them again and again in BGP. This will be, I guess the best word is an introduction to route maps, just to get the general feel of what they look like and how to use them. Now, if you haven't seen them before, they're kind of like basic programming. Now I'm talking about the language basic, and I don't know if you guys remember that programming language. I remember it from back when I had my Commodore Amiga 1000, and I was learning how to program in basic, and I type in line 10. Echo, hello world. I can't even remember like all the specific syntax. But then line 20 would be go to 10, and it would just, run the program, and your screen would fill with this hello world, and then you're like, yes, I am a programmer. That's kind of what the route maps are. It's like programming for Cisco routers. You have sequence numbers, so in a sense, it's a little bit like the new advanced access list. And it's just a compilation of if-then statements. I don't know how much programming experience that you have in your past, but if-then statements pretty much said if this criteria matches, meaning if this variable equals that, or they hit the enter key, or if this, then go ahead and do that. But in the Cisco router world, they call them match set statements. You can kind of see my example down here. I'll get into the specifics in a moment. We have like match blah, that's some criteria. It could be a certain route type, it could be a certain routing protocol, it could be a certain interface, it could be just about anything. I'll show you some of the match criteria in a moment. If it matches that, then do this, and that could be setting the metric, setting the route type, setting a filter to keep the route from going across. Could be many different things, and we have all of these match then statements with sequence numbers. It will work through the sequence numbers in order, just like an access list. So let's say a routing update comes in, whoop, routing update received. If we have a route map applied to them, it's going to say, okay, are you this? Are you that? Are you this? Are you that? It's going to go through all the match criteria that exists, and if it doesn't match, then the route map just doesn't apply. That's the difference from the access list. The access list world, if you don't match, you are specifically denied. You are not passing go collecting $200. In a route map case, if you don't match, then the route map just doesn't apply. All these special things, the thens that you have, aren't going to happen. So you're going to essentially pass through unmodified. So that's what the route maps are all about. Now, before I get into the specifics of the syntax, this is used heavily in BGP. Like, without an understanding of route maps in BGP, you are very limited in what you can do. It's also used in something known as policy-based routing, and of course, the one we're going to talk about here, route filtering. But I don't want to just leave policy-based routing unturned. Policy-based routing is a type of routing that you can essentially apply any sort of criteria to an interface that you want. Let me give you an example. I could have a router, and maybe I have one internet connection that is a T3 line and another internet connection that's a T1 line. Now, both of these connect to the internet, but I want, I've got two default routes that point out, but I want maybe the, management and accounting, the people that really need the internet to get the T3 line, but the rest of the general employees that would just be surfing the internet for fun, well, they're all going to share that 1.5 megs of bandwidth on the T1 line. What I could do is create a route map that, this is just a name, and I could say match. If you're this subnet of people, then I want to set your next hop IP address to be that ISP. But if you're this subnet of people, then I want to set your next hop IP address to be that ISP. Does that make sense? So based on the subnet that these people are coming in on, or you could do it based on if you come in this interface, then you get this. If you go in that interface, the match criteria are very flexible. You have a lot of options there. So you can match these people based on just about anything, based on the type of traffic they have. You know, if you're using Kazaa, I want to send you out the T1 line. But if you're just doing normal web surfing, I'm going to send you out the T3. Give you a lot of options here because I want you to see that policy-based routing is very flexible. And that's where route maps come into play. But what we're going to talk about in here is the route filtering world. Before I leave this slide, I want to talk about the general syntax of the route maps. The route maps are created from global configuration mode. You do it by typing in route map followed by a logical case-sensitive name. Jeremy not being the best name available to you. You want to have a kind of a general name that gives a feel for what the route map does. Then we have permit or deny statements. You can see that I have permit, in this case, sequence number 10. This is the sequence number. If you don't type in a sequence number, the default sequencing is 10. Matter of fact, let me bring this up on a live router here. Get this somewhat centered in the screen. I'm going to go on router 3 and just type in route map followed by the name. I'll put Jeremy just to show you your options here. Notice you can just hit enter right after that. If you do hit enter, it automatically will do a sequencing of 10 and with a default of permit. So that's a nice quick way to create a route map. I'll do a show route map. And you can see that I have Jeremy permit sequence number 10, match clauses and set clauses, which are nothing because I haven't typed anything in yet. Now I've got permit 10. Notice I have match something. I've got some criteria there, blah, set, blah. From there, I create a second entry. Maybe under here I'm matching, if I see this kind of update, I'll do this. Now, sequence number 20 right below is also permit. I have match blah, space, blah, space, blah. Again, I'm leaving it general because those are individual criteria. If I say, for instance, match, we could put like an access list number. Match the IP access list 50, 60, and 70. And in each one of those, okay? If we were to put the match statements like that, they will end up becoming logical ORs, meaning I will match the updates in access list 50 or in access list 60 or in access list 70. Now that's handy because if you have got a bunch of criteria that you want to match and it doesn't really matter that all of it matches, you just want, maybe this or that, it could be match, this access list on this routing protocol. I'm trying to fill in things for the blah, but I'll just leave it general for now. If you put multiple entries on the match on a single line, it becomes a logical OR. Now, do me a favor. I'm going to jump down sequence number 30 and just look at 40 because we can also type them on multiple lines. Match blah, enter, then match some other blah. If you do that, they become logical ands. See how it's like a programming language. There's all these unstated rules that just sort of happen. So if I put, match access list 50, right here, and then I say I also want to match the routing protocol OSPF or interface serial 0, then it becomes an AND. So it's going to say match these updates coming in serial 0. Whereas if I would have done that here, it would have said match these updates or match things coming in serial 0. You see the big difference. Now, the last thing I want to talk about with the syntax is one of the more confusing ones, in my opinion, and that is the deny statement with a route map. I can type in route map Jeremy deny 30. And what that does, in this case, it's just sequence number 30. A deny statement says anything that you match under here will not be processed by this access list. You might say, well, I want, routing updates from OSPF to be processed, but maybe just the ones that are in access list 50, I don't want to have this route map apply. Well, then you can do a deny statement. I can say deny these specific updates from being affected by the route map. So most of the time, you'll be using permits with the route maps. Deny is your block statement. The reason it gets really funky and confusing is because you also have the ability to permit and deny in like an access list. So I could say have a permit statement here and then match an access, we'll say match access list 50, which inside of that access list I have a deny statement. So you're thinking, okay, I'm permitting a denied access access list statement, or I'm denying a permitted one. So it gets kind of confusing when you start combining the denies and permits. We'll get more into that as we get more advanced in the route maps. For now, I just wanted to show you the general syntax of what it looks like. So let me show you an example of the flexibility that route maps provide for you. Same story. We have RIP over on the left, OSPF on the right. We've got the 1 through 10 networks that are being sent from router 1. I've removed all the distribute list commands from before, so we are receiving the full routing table on router 2. Let me bring that right up here into the screen so you're able to verify. You can see router 2, I just went in and did a no command on the distribute list. So router 2 is now receiving everything. I've even turned off the redistribution between router 2 and router 3. So we're back at a fresh slate. Now here is how route maps can be much more flexible than just doing distribute lists. Let's do this. I'm going to go into global config mode and let's create a couple access lists on router 2. We'll do an IP access list, standard access list, and we'll call this net 1, 2, 3. Okay, and in this we'll permit, let's see, permit, yeah, I'm kind of creating this as I go. 10.50.1.0, 00255, 2.0, and 3.0. We're going to let the implicit deny catch everything else. I'll create a second access list and do net 4 through, if I could type, 4 to, let's do 6. And again, I'm going to go in and do a permit 4, 5, and 6. Let the implicit deny catch the rest. All right, for now, that's our two access lists that we'll use. You also have to remember that they are case sensitive. So now we can get into the route map configuration. I'm going to type in route map, and we'll name this route map flexible, because that's what these things are. And we'll just leave the default. We'll do a permit 10, which is the default if you just hit enter right there. Now you can see when I hit the question mark, our only real commands that we have under here are match and set. The rest of them are just kind of fluff commands, description, default, exit, all of those kind of things. So what I'm going to do in this case is I'm going to say I want to match. And then you can see a bunch of things that we can match, most of them dealing with BGP. You can see autonomous path, the BGP community list, BGP VPN extended community list. You know, there's a lot that deals with BGP, but there's also some things that deal with OSPF. For instance, like metric or route type, the tag, that's an OSPF thing. Metric of the route goes for all routing protocols. In this case, I want to match those access lists I just created. So I'll type in match IP space, and then here's my flexibility. I can match an address. I can match the next hop, like if there's a certain packet destined for this next hop, or from a certain route source. I'm going to say match the IP address, and now it's going to give me the option. It's going to say, do you want to type in an access list number that identifies these, or an access list name? I'm going to scroll back up, and I'm going to say, I want to match the IP addresses defined in net 1. Did I miss? I was going to, I have 1, 2, 3. I highlighted 4 to 6. I don't know why. Actually, I just completely filled in the wrong command there. Match IP address, net 1, 2, 3. There we go. So we've got the first match statement in there. Now we can start doing our set commands. So I'm going to say I want to set, in this case, and here's all of the options that I have. I've got the BGP AS path. I've got community lists, all of these different things. Again, mostly dealing with BGP. But look at this. Set the metric. I want to set the metric for those 3 networks, 2, and you can see I can add or subtract what the current metric is. I can type in a specific metric value. Notice it says a specific value, or you can set the bandwidth in kilobits per second. That's if we were trying to set the metric for EIGRP, where it has multiple pieces that creates the metric. In this case, we're using OSPF, and I'll say I want to set the metric to, for these, let's do 50,000. Okay. Hit enter. I also want to set, let's do the metric type. Remember, OSPF has the different types of routes, and we're going to say this is going to be some type 1 networks. Enter. Let's exit out of that. Now let me do a show route map right there, because I want you to see that we now have a route map called flexible, permitting sequence number 10. It's matching the IP addresses in net 1 through 3, so 10.50.123.0, and it's going to set the metric to 50,000 for those routes and the type to type 1. Now let's continue on. I'm going to go in and I'm going to say, let's do a second one. Route map, flexible. Again, same route map. We're just adding more lines to it. I'm going to say permit, let's do sequence number 20. So we're adding the second line in here. Now, in this case, I want to match the IP addresses that are defined in net 426. That's the second range that I put in there. And I'm going to set for those the, let's go ahead and set the metric to be 10,000. So we're going to actually set the metric lower for that group. And we're going to set the metric type to be, let's use type 2 this time. Okay, so we've got a little flexibility defined in there. We've got two different types of routes, or two different groups of routes that I should say that we're matching. Now, I want to stop right there for a moment and just do a show route map to show that this is flexible enough to now divide the networks that we're redistributing into OSPF into two groups, to set them with different metrics, to assign different metric types. Now, let's also talk, what if we wanted to deny some routes? I didn't create an access list for that, so let me do it. IP access list, standard, and we'll say deny network 7. Deny 7 will be the name. And all I'll put in here is to deny 10.50.7.0 and permit everything else. Now I'm jumping back to my route map. Watch this. I'm going to say route map, and the name was flexible, permit, or actually, I almost typed it. I'll put deny 30. Okay. Now here, watch what happens here. Oh, you know what? I just did that backwards. This is where the logic gets you in trouble. I'm going to go back and I'm going to kill the access list. No IP access list, deny 7. Go back in. Here's where it gets you in trouble. You see this? I'm going to type in under this access list, permit 10.50.7.0, 0.0.0.255. And then we'll let the implicit deny catch everything else. Now I'm going to go back in, and then I'll explain what just happened there. I'm going to go back into my flexible route map, and I'm going to say deny 30 match IP address, and we'll do deny 7. Enter. The reason I did that, the reason I first, well, let me say why I fixed it. The reason I fixed it is because the route map is making a statement of deny. Deny. So I'm saying I want to deny the things that I'm matching below here. I want to prevent them from happening. So then I hit the match IP address deny 7, and underneath that I have the way I fixed it was to put permit 10.50.7.0. Now I feel like I'm stumbling over my own words. Let me see if I can explain this a little better. I am permitting the network to be denied. Do you catch that? We have the route map flexible, deny 30. So I'm saying this is a deny clause in, my line of basic, my if-then statement. This is a group of things I want to deny. And what do you want to deny? The things that are listed in deny 7. Now let me talk about what would have happened if I would have left it like this. What if I would have left the deny statement in here? Well, in this case, two negatives equal a positive. I'm saying I want to deny the address is listed in access list 7, and then it says, oh, deny this one. So I'm essentially denying a deny statement, which means I'm going to allow it. If that wasn't confusing, I don't know what is. But just think of it as multiplication. If you multiply two negative numbers, what do you get? A positive. In the same sense, we're denying things twice. We're saying deny, everything under here is denied, but then I'm saying, except this, I'm denying that from being denied. I think that's the best way I've said it so far. I'm denying 10.50.7.0 from matching the deny statement. But what does match? Everything else. Do you see what's happening here? I'm saying deny 30, but permit anything. So everything is being permitted to be denied. Ugh. Shake your head a couple times on that because that's the weirdness I was talking about when you get into those route maps and the permits and denies and combining them together and how those two things link up. That's what we're doing right here is in this case, we are permitting the 10.50.7 network to be denied in the route map. Now, could you flip that? Could you do a permit on the flexible and then a deny in the access list? Absolutely. It works fine that way. You're combining a positive and a negative together. It's like a battery. The two have to match. Otherwise, you're really just, kind of undoing what you're doing. All right. Enough on that before I blow my own mind again. All right, so we've got the route map flexible deny 30. Before I add the final statement to this route map, I'm going to do a show route map. And you can see it's growing. Sequence number 10 is to match these guys, set the metrics. 20, match these guys, set the metrics, set the metric type. Sequence number 30 is to deny the things that are in the access list, deny 7, which lets me know I've got that access list permitting the 7 network, 10.50.7, to be denied. Now, the last thing I'm going to do in here is type in route map flexible, and we'll do a permit 40. Underneath here, I'm just going to do some set statements. Let's say set the metric to 500. Set the metric type. Let's go ahead and make the metric type 1 again. Exit. Now, what that does, when I put a route map statement with some set clauses without any match, like this last statement right here, is it acts as a match any. Just like an access list, if I would have ended the route map right here, it would have matched this, net 1 through 3, net 4 through 6, and then deny 7, and then said, well, nothing else matches this route map, so I guess we're done. But by putting in a statement at the end that just has a blank match, you don't even need to have set clauses under there. This says permit everything else. In this case, I'm permitting everything that didn't match these first 3 sequence numbers to get the metric set to 500 and the type to 1. Whew, this route map is intense, isn't it? With that being said, let's kick on the redistribution between router 2 and the OSPF domain, apply the route map, and watch what happens. I'm going to go, in this case, into router OSPF 1. And I'm going to type in redistribute rip. But instead of putting all my metrics, my metric types, I don't do any of that. This time I'm going to attach a route map. I say redistribute rip according to the route map flexible. Link, we just link that up to the domain. At that point, I guess we can put in the subnets if we want to make sure those comes through as well. But we're done. The route map takes care of everything else. And what's happening now is that route map is going to be matching all of the different routes that are coming through and setting all of the things that I have here. You ready to test it? You ready to see if it worked? The way to do that is to go through to router 3 and see if all those criteria that we set are happening. So I'm over to router 3. I'm holding my breath. Show IP route. Whoo, Nelly. Look at that. I just felt like a Western cowboy there. We've got 10.50.1, 2, and 3. Nets 1 through 3, right? Look at them. Look, isn't this beautiful? This is bringing a tear to my eye right now. Look at this. We've got external type 1, the type that we chose, so the metric is incrementing. Remember, external type 1, the metric increments, and the metric happens to be 50,000 plus 64, which just happens to be a T1 link between router 2 and router 3. That's a cost of 64. So it accurately added that on there. Second set of routes, 50.4, 5, and 6. The metric is set to 10,000, external type 2 routes, right? Let's scroll back up, verify, that's exactly what we wanted. Net 1 through 3, there's our metric, metric type. 4 through 6, metric, metric type. What about this one? Sequence number 30, deny 7. Let's scroll back down. Where's network 7? Oh, I get excited at this. There is none because the route map killed it. It caught it. It was permitted to be denied by that route map statement. And finally, the rest of them, 8, 9, and 10 match sequence number 40, which set the metric to 500, and the type to type 1. External type 1, it added the 64 of that T1 line to our original 500. Oh, man. It's beautiful. I know you're thinking right now, you are a freak of nature. How can you get so excited about that? But I'm telling you, that kind of flexibility is what people die for in the Cisco world. Maybe not that extreme, but in like think of the CCIE lab when they're trying to get you to do left, right, just dance around all these routing tables. These route maps just do beautiful things. So that is the tip of the iceberg of what you can do with route map. That's a perfect example of using it in redistribution to apply different criteria to different routes that are going through. All right, last topic, and I know we've run a little bit long, so I'll make it a quick one because it's very rarely used. It's using the administrative distance. Now, little review from the CCNA. Administrative distance is the believability of routing protocols. You might remember that things like RIP has a believability of 120, OSPF has a believability of 110. So if your router receives routes from different protocols, it says, well, which one's more believable? Oh, EIGRP is. Let's go with that. And you can see sometimes in rare cases, very rare, we may need to tune the administrative distance or change it for routing protocols or redistributed routes. Here's a scenario, a very weird one, where that might happen. Notice we have OSPF that's running across the T3 link. So we have, some sort of administrative divide in our organization where half of it runs OSPF and the agency up here refuses to convert to EIGRP. Maybe they're different vendor routers. So they're running OSPF and they control the T3 link and they're linked up over here. And actually, it couldn't be different vendor routers because they're also running EIGRP on the bottom. So just some policy has prevented it from happening. So here's what happens. We want to redistribute these routes, the 10.1.x routes, into the EIGRP world because we want redundancy. If the T3 link goes down, we want all of the traffic to be able to cross the EIGRP domain to still reach those networks up there. But here's the problem. I redistribute those into EIGRP. They flow over here. They flow up here. Now, obviously, the T3 link is much better than these links down here. But it doesn't really rely on metric until it has a tie in administrative distance. So this router has a big question. It's like, which one do I use? We've got OSPF saying go this way and EIGRP saying go this way. Well, what it's going to rely on is the administrative distance. In this case, EIGRP has an administrative distance of 90. So it's going to believe EIGRP long before OSPF, which has an administrative distance of 110. Now, likewise, we don't want, maybe there's these networks up here being advertised. We don't want those networks to come up here and, they get advertised in OSPF so that we've got redundancy there. We don't want people to have to, cross the, to reach this over here, to cross the OSPF link and then come down this way and loop back around because we make OSPF more believable for everything. Do you see the dilemma here? We've got a mess in our hands. The solution should be to just nix OSPF or nix EIGRP and choose one routing protocol. But what if you can't for some political reason? That's where we can tune the administrative distance. It's actually very simple. All we need to do is go into the router that we want to tune it on. In this case, it would be this router up here. Now, this is just a logical example. We're not going to have a complete end-to-end scenario here. But what we would do is go into this router. We'll say this is router 3 for convenience sake. Okay. And, oh, we're on router 3. So I'm going to go into global config mode and go under the OSPF process. Well, there's actually two ways to approach this. You could either tune OSPF to be lower or tune EIGRP to be higher than OSPF. In this case, I'll focus in. Whoa, I don't know what I just did there. There we go. I'll focus in on OSPF. And so OSPF, I'll jump under the process. And the command to do this is just distance. And you type in what you want the administrative distance to be. So I'll say the distance I want for OSPF is 85, which is going to be lower than EIGRP. Now it's coming up and saying what source address. Now this is going to be the source address of the neighbor. meaning I can set the administrative distance lower for just routes coming from this neighbor or just routes coming from this neighbor over here. So you can actually choose what neighbors you want. In this case, I would probably type in this neighbor, or I could just say for all neighbors by typing in a source address of that with a wildcard bit of that. It's just like an access list. That's kind of like a match everything. So all neighbors that are running OSPF will have their routes set to an administrative distance of 85. From there, we can add on an access list. If we just hit the enter key, that's kind of dangerous because immediately all OSPF routes get their administrative distance lowered, which means OSPF would become the more believable protocol for everything. In which case, this router, if it was trying to reach this network, instead of just going across that T1 line, it would say, oh, OSPF's more believable. I'll hop that way, then I'll go that way, then I'll go that way, then I'll come back over here to this network. This thing's turning into a mess, isn't it? So what we would want to do is create an access list that just matches the routes that we want to tune the administrative distance lower on, which in our case would be, whoosh, whoa, got a little crazy there. Sorry, used the mouse instead of my pen to circle that. These routes. These routes I tuned to be an administrative distance of 85, so when this router had to decide between using EIGRP to reach them or using OSPF to reach them, it's a no-brainer. OSPF beats EIGRP's 90, so it's going to choose that way, but only for those routes. All the other EIGRP routes are going to be more believable because we haven't tuned the administrative distance for those. We would just create an access list that would match just those routes. So that's tuning the administrative distance. I didn't want to get into a full-blown scenario because it's just not done very often. Forgive me. I really try to keep the videos at around 45 minutes or less because I know sometimes when you're sitting there, you get a little antsy. It's hard to sit there for much more than 45 before you got to get up and stretch. But hopefully the coolness of the route map kept you going because I'll tell you what, route maps are just downright awesome. So to hit the high points and not make this any longer than it needs to be, we did look at using distribute lists, which simply apply an access list to what routes get distributed using a routing protocol. From there, we looked at the flexibility of route maps, and don't worry, we're not done with them. Plenty more of that to come in BGP. Finally, we saw administrative distance, which very rarely used, but you can actually tune down that table of administrative distances for all the routing protocols to fit whatever needs you have. I hope this has been informative for you, and I'd like to thank you for viewing.